Previously, we learned how both nozzles and adjuvants have an impact on droplet size. We discussed details about nozzles, and now we will explain more about adjuvants.
And adjuvants play an important role in all three phases of that application process. We're going to start out with the atomization part. A lot of the adjuvants that we use for the atomization aspect are drift reduction adjuvants. And there are three main types of drift reduction adjuvants. The first one are viscosity modifiers. They modify the viscosity, increase the surface tension, which means when the spray is atomized, we form larger droplets. We reduce the formation of those small droplets that are more prone to drift. There are two main types of viscosity modifiers: synthetic polymers and organic polymers, the guar gums. Another type of drift reduction adjuvant is oil-based. These also work to try to reduce the small spray droplets created during the atomization process, but they don't affect the viscosity as much. And the third type is invert emulsions or encapsulators. They work to create an encapsulation process that also helps to try to make more of the spray droplet spectra all relatively the same size. Adjuvants also have an impact on the transport phase of the application process. As those droplets travel from the nozzle to the target, they're affected by the weather conditions. Particularly important are the temperature and humidity. As it gets hotter and drier out, we have an increase in evaporation. This doesn't play a big role with really large droplets. They're fairly resistant to the effects of evaporation, but our smaller droplets, as they travel from the nozzle to the target, begin to evaporate. Droplets of a certain size might get reduced in size to a point where they may have left the nozzle large enough to not be driftable, but as the evaporation reduces their size as they travel from the nozzle to the target, they get to a point where they are now small enough to be blown off target. Or worse yet, we'll lose them completely. They evaporate completely, and we don't get any of that product containing those droplets down to the target. So adjuvants can help us protect the droplets as they go from the nozzle to the target. The third part of the spraying process is the deposition phase, where we've atomized the droplets, they've traveled to the target, and now we want to get them to deposit on the plant. And a big part of the deposition process is retention. When the droplets impact the target plant, we want the spray to be retained on the plant surface. Many times what happens is those droplets bounce or roll off the plant. So they may have been atomized and made it to the target, but they don't actually deposit and stay on the plant. Thus, there's no uptake of the pesticide into the plant. Some of the adjuvants, surfactants, can be used to reduce the surface tension so that droplet will spread out when it hits the target surface and reduce the likelihood that it bounces or rolls off the target. Spreaders help spread that droplet out on the surface area of the leaf, again, to help increase the uptake of the pesticide from the droplet into the leaf. Stickers can be used to help make that spray solution, that droplet, stickier so that it stays on the plant surface. Again, the whole goal here is to achieve retention when that droplet deposits in the leaf. We want to reduce the chances that those droplets bounce or roll off the plant. And many times the things that we do to decrease our risk of drift, i.e. increase our droplet size so that they're more resistant to being moved off target, actually increases the likelihood of that bounce or roll off, because it's the larger droplets that are more prone to bouncing or rolling off the target surface. In many cases, we can use an adjuvant to tweak the droplet size that's been created by that nozzle to help better the ideal droplet size that we need for that application. You have two examples. Let's say we're making an application that we need a lot of good coverage. It's maybe a contact fungicide, so we know we need a smaller droplet spectrum. Coverage is important, so we're going to want small droplets. Let's say our ideal droplet size for this is 300 microns. We know that when we make a 300 micron droplet size, we're going to have some droplets that are smaller than this, so we've got this maybe a higher risk of drift than we would with a much larger droplet spectra. We can use a drift reduction adjuvant to help reduce those fine droplets. So we're going to select our nozzle that produces that VMD of around 300 microns, but we'll use the adjuvant to help try to reduce further those fine droplets. Another example would be the flip side. Let's say we're applying a herbicide where drift is a primary concern in our application. So we're going to be trying to make really large spray droplet sizes. So we would pick a nozzle type size and pressure that provides a large droplet. We can use adjuvants then to help us in that deposition and retention phase. We know that we need to make these large droplets to try to reduce the risk of drift as much as possible, but we're also aware that those really large droplets have a much harder time depositing and retaining on the plant surface. So we'll add adjuvants to help with that deposition phase to make sure that what we do get down to the target, we can keep it on the plant leaf and get that pesticide from the droplet into the plant. It's important to realize, though, that not just the adjuvants have an impact on the droplet size. The pesticide formulations themselves can have an impact on the droplet size. Is it an emulsifiable concentrate, soluble concentrate? All these different types of formulations do have an impact on the droplet size, as well as the carrier. In many cases, we use a fertilizer in addition to or a substitute from water as the carrier. That can affect droplet size. It can also have an impact on that transportation phase. You might also be protecting droplets from evaporation when you add those products to the spray solution.